Okay, we are live now. So ready? Let me. Okay, welcome everyone to Harvard CMSA Quantum Matter Seminar. We are very happy to have Rahul Sahay from Harvard University, who will speaking about quantum spin legs. And let me remind the audience, please feel free to ask questions, interact with Rahul, and hopefully we have a fun time. And let's welcome Rahul. Please take over, it's yours.
Okay. Thank you so much. Yeah, thanks, Driven, for the introduction and for the opportunity to speak. Yeah, I'm super excited to talk to you guys today about a archive preprint that I recently put out with two really wonderful collaborators, my advisor, Ashwin Vishwanath, and a HQI postdoctoral fellow here at Harvard, Ruben Veraisen. And this talk is really going to be focusing on highlighting a kind of interesting regime of non-equilibrium quantum dynamics that's interesting in its own right, but also sort of provides a streamlined route towards realizing some very interesting phases of matter in current quantum simulation experiments. So with that, and we call these the states that you prepare using this quantum spin lakes. So with that, let's dive right in. Yeah, so maybe the best way to kind of motivate my talk, as a young member of the community, I can say that Emergence is really quite fantastic, and it's really quite remarkable. The kind of plethora of phases of matter that have sort of been understood over the last 40 to 50 years that can emerge from many-body quantum systems. So in particular, we've discovered topologically ordered phases, interesting SPT phases, gapless phases, in this case, a gapless quantum spin liquid, but more broadly, and also fracton phases of matter recently. And I think the thing that's really beautiful about all of these different phases of matter is that on one hand, they're extremely fundamentally interesting. So they're related to kind of rich mathematical structures such as topological quantum field theories and also fundamental objects like deconfined phases of gauge theories. But in addition, these phases are extremely practically interesting. And most of them, can have a potential application, and kind of emerging quantum technologies. So, despite all of the interest in these phases of matter, I think the key problem that I want to be talking about today, and the problem that I've been thinking about for a while, is we know of a lot of very interesting phases of matter, but realizing them in the lab is really quite challenging. So in particular, for the case of topological order, we know of one really amazing example, which is the fractional quantum Hall effect, which has really been completely unambiguously identified in experiments, ranging from transport experiments to shot noise experiments, and more recently, some really beautiful demonstrations of anionic statistics and interferometry and scattering experiments. But outside of the context of the fractional quantum Hall effect, I would say that the situation is much less clear. So in particular, there's a large zoo of topologically ordered phases that have not seen any experimental signatures, but I think even experimental signatures that have been seen, they're sort of not up to the really, really high standard of the fractional quantum Hall effect, though that is an extremely high bar, and there are really promising directions in this. And so a natural question you might ask is, why is it so hard to realize, topologically ordered phases of matter? And in a broad set of circumstances, the reason is because in some sense, the requirements for realizing them in equilibrium is extremely restrictive. So I think a good way to sort of get a sense for why this is true is to take a very concrete example. So the simplest example of topological order in 2+1D is the Z2 quantum spin liquid, or Z2 topological order, which you can think of as the deconfined phase of an emergent Z2 gauge theory. So I think the best way to kind of gain some intuition on this is to first think about the fixed point wave function of the Z2 quantum spin liquid, which is the so-called toric code wave function. And it's a little bit of a caricature of what the state is, analogous to like the all-up state for the ferromagnet. So to kind of get an understanding of this, let's think about qubits on the links of a square lattice, and we'll treat the spins as a Z2 valued electric field. So for example, an upspin will have no Z2 valued electric field, and a downspin will have one. And with this, we can sort of play games that we play with in electromagnetism. So we can define like a divergence out of any given vertex. So in this case, there's a zero divergence of the electric field, and if that's true, you only form closed loops. In addition, by acting the X operator on the system, you can get a divergence that's non-zero, at its endpoints. So this sort of signals that these endpoints, the things that are created by the X operator, carry, Z2 gauge charge and are called E anyons. In addition, it's not so hard to convince yourself that the thing that you'll create, if you act Z operators on this system, is a Z2 flux. So it'll act like a flux for the charges, and we call these M anyons. So the deconfined phase of the Z2 gauge theory, or the emergent Z2 gauge theory corresponds to this toric code wave function, which consists of all possible closed loop configurations of the electric field. And these appear with equal weight and equal phase. And the state is also characterized by the existence of no condensed charge or flux in the problem. So let's try to ask ourselves, what sorts of terms in the Hamiltonian need to be, there in order to realize this as your ground state. And it turns out these two terms are really quite restrictive. So the first one is kind of strong local constraints to give us, constrained Hilbert space. So, or something like a Gauss's law. So for example, we could add this term ZZZZ, around a vertex, and that would, give us this constraint that, electric fields must appear, have divergence 0 mod 2 around any vertex. So the nice thing about these local constraints is actually they're kind of ubiquitous in condensed matter systems. So they can appear whenever you have, either geometric or interaction frustration. And there are two-body terms, in nature that you can have that sort of impose these sorts of like Gauss law-like constraints. And the thing is, with only these terms in the Hamiltonian, you end up getting a really large number of low energy states that all satisfy the Gauss's law. So in other words, if you only had this, star term in your Hamiltonian, you would have a lot of low-lying Gauss law states. Does someone have a question? I think someone's unmuted. Oh, okay. Awesome. So yeah, the next ingredient that we need is really strong quantum resonances between these Gauss law configurations. So in other words, we need terms in the Hamiltonian that connect these Gauss law satisfying states. So an example of such a term, as all of you are probably familiar with, is the plaquette term in the toric code. But the plaquette term, I think, is more tricky to realize, sort of experimentally. So if you think about it, these terms, typically states that satisfy the Gauss's law are different from one another by several local rearrangements. And so the only way to sort of generate these plaquette terms in the Hamiltonian is sort of perturbatively. So in other words, if you have an on-site field like X, you'll see that that doesn't commute with the Gauss law. And so, if the Gauss law is the largest term in the problem, then, you'll generate this term at fourth order in perturbation theory, which is the plaquette. But what that means is that the plaquette terms, the things that precisely stabilize the massive quantum superpositions, in the toric code, for example, are not typically not strong enough in experiments to like beat confining fields, to be over confining fields. So the thing I hope to show you today is that non-equilibrium dynamics can provide a kind of robust route to realizing the sort of delicate superpositions that you would need, for these, interesting quantum spin liquid-like states over finite-sized regions, even when the ground state isn't a quantum spin liquid. So even when you don't have resonances in the problem. So, it's kind of, yeah.
Yes, Rahul.
Uh-huh.
This is just a minor point, but can you just maybe just say a few more words about how there are some terms that you generate perturbatively, right?
Mm-hmm.
Can you just I think that's kind of a bit quick.
Oh yeah, of course. So okay, I guess what I mean to say is that let's imagine that you have some local constraints, in some spin system, and as a result, every state that satisfies those local constraints is kind of low energy at this point. So for example, in the toric code, all closed loop states are kind of low in energy, right? Then, in order to connect these states, in order to stabilize superpositions between these states, the things you need in your Hamiltonian are things that will, you need terms that connect them, right? But typically they differ by lots of local rearrangements. So in other words, one closed loop configuration, in order to, move it to another closed loop configuration, you need to flip 4 spins. That's what this formula is saying, right? That's what the plaquette term is saying, right? So in order to generate that from just 2-body terms or 1-body terms, in your Hamiltonian, you typically need to go to very high orders in perturbation theory, right, in order to generate these resonances, right, in your problem. Does that sort of answer your question, Juven? Like.
Oh yeah.
Okay,
I,
wonderful.
I wonder, I'm not sure whether I should make the comment, but I think the other collaborator, Ruben,
Ruben, yeah, everything's icing.
everything. So how's that, that based on that perspective? So everything starts from icing model and you add the interactions.
Yeah, that's true. So yeah, I will say everything is icing is a really cool kind of story. So there you kind of take advantage of the fact that you have, so I'll say that you take advantage of two things. One, you take advantage of the fact that you have larger local Hilbert spaces, but also the structure of your on-site fields is very rich in that case. So, everything is icing, you have diagonal interactions, and you have a very rich structure for your on-site field that's able to sort of do these sorts of things for you. Yeah, this is just some intuition, but I agree. Like this is just kind of a heuristic discussion at the moment. Does that
Sorry, Rahul, would you mind telling why is that the case that the geometric or interaction frustration like naturally gives rise to this four-body set Hamiltonian?
Yeah, that's a good question. So I don't mean that it gives rise to a four-body interaction, but what I do mean is that, so typically imagine that like you had something like actually, you might be familiar with the Rydberg blockade, for example. So if for those of you that aren't familiar, the Rydberg blockade is literally just strong icing interactions, like just ZZ, nearest neighbor, or like, to some distance. And basically, or it's like NN actually, right? And those things can kind of lead to these similar local constraints, right? As the ones in the toric code, right? So that's an example of how, yeah, does that kind of answer your question? If, for example, if I had strong NN, blockading some distance, then that means that, no two atoms that are within those distances can, be excited, and you can generate these sorts of, local constraints as a result, right? That is a local constraint in some sense. Does that answer your question?
Yeah, I see. So this is kind of the magic of mapping, for instance, in that paper, and Misha group, like of the excited Rydberg and the what was it, like lack or presence of a dimer or something, and that's how we can. Okay, I see. Okay, cool. Yeah, thank you so much.
Yeah. So another example that might be more familiar to people is like, when you have like just antiferromagnetism in a triangular lattice, right? That even gives you sort of local constraints on your triangular configurations, right? You want to form like, oppositely aligned things, but like you can only form, you can only form certain things to be, singlets and not other things to be singlets. And that's sort of a local constraint on your problem. Like in other words, there's one singlet dimer touching every vertex. Like that's an example. Yeah. Thanks for the good question. So yeah, in any case, what I'll show you is that non-equilibrium dynamics can prepare these sorts of interesting, interesting states, even when you don't have resonances in your problem, or even when your ground state is not a quantum spin liquid. Crucially, these things are finite size quantum spin liquids, right? So they only extend to finite size. So we'll call them quantum spin lakes, which is actually, I think, a place in Danvers, Iowa, or something like this. A spin lake is, I guess. And the reason we call it a lake is because, a lake is a body of water, usually fresh water, of relatively large size contained on a body of land. And a quantum spin lake is a body of quantum spin liquid, usually close to its fixed point, of relatively large size contained in a finite size system. So, with this, let me add a little bit of extra motivation. So far, this has been pretty, maybe like from a purely theoretical perspective. But I think, one reason why, trying to look for ways in which non-equilibrium dynamics can prepare interesting states of matter is because why that's like kind of interesting and natural is because real-time dynamics is extremely natural on, a kind of emerging, experimental platform, which is analog noisy intermediate scale quantum simulators, or NISQ quantum simulators. So this was a term that was coined by John Preskill in 2018 to describe, a really wide range of, quantum devices that are sort of around these days. So just to name a few, there are ultra cold atoms, in optical lattices. There are Rydberg tweezer arrays. There are trapped ions and things like this. And what these, experiments let you do is they let you build up systems, atom by atom, and have really detailed knowledge of the Hamiltonian inside of the system. And you can get really tunable Hamiltonian parameters, tunable lattice geometries, which is very exciting. And in addition, something that's exciting for the probing of topologically ordered phases right, is access to both local and non-local observables. But the thing that's challenging on these devices is actually going to the ground state generally. So, the ability to sort of realize interesting phases of matter through non-equilibrium dynamics, really, gives us, enables us to engage with, exotic quantum orders in near-term experiments. Yeah. So awesome. So what I'll start off with is my talk will be structured into sort of two parts. So the first part will be mostly centered around understanding the sort of non-equilibrium mechanism. So in particular, just to kind of give you a flavor for how it will end up working out, is we'll start off in a phase where there's a lot of E anyons condensed in the problem. And this phase will be a trivial phase. So it's not as interesting as a quantum spin liquid. And what dynamics will effectively do is it'll effectively project out condensed E anyons in the system. So it'll effectively get rid. So, this is a, since you can think of E anyons as gauge charge, this is effectively un-Higgsing the state, in that sort of parlance. And this is what, enables it to sort of generate these really interesting states of matter. In some sense, it's a subtractive way of generating, kind of interesting phases of matter. And then the second part of my talk is that I'll motivate how, the stuff that I'm talking about is connected to recent, Rydberg atom experiments. And at the very end, I'll introduce this pretty cool, novel numerical tool that we sort of motivated by using the theory that we developed. So it turns out that there's a numerical tool that you can use to kind of reproduce the experimental data, seen in like the Rydberg atom experiment, and potentially, aid in, future experiments at a fraction of the time of, kind of full scale numerical simulations. So yeah, with that, let's just dive right in. Okay. So yeah, so let's try to understand this non-equilibrium mechanism. And the way we're going to do so is let's pick a very concrete example. So we'll start off with what I call the deformed toric code model. I don't know why we ended up calling it that, but it's just the toric code in a field. But crucially, so it has its Gauss law constraint, but crucially, we'll get rid of the resonances in the problem. So, if you have strong resonances in the problem, the ground state will be a quantum spin liquid, which, is a little bit, kind of cheating. So what we're going to do is we're just going to get rid of, the ground state quantum spin liquid more or less by getting rid of resonances in the problem. And then we'll have two on-site fields. So the first of these you'll see is an X field, and that will generate E anyons, right? Because it doesn't commute with the Gauss law, so it generates Gauss law violations. And then the second term here is a Z term, and this will generate M anyons. And what we'll do is we'll always take Hx to be equal to 1. So that will be our normalization. And we'll investigate the ground state phase diagram, so which will give us some intuition as to what is going on in the system. So we do this by using cylinder DMRG to get the ground state phase diagram, and it looks something like this. There are three really nice phases that appear. And the x-axis here is the Gauss law. So it tunes from 0 to 4 in this case. And the y-axis you'll see is this M generation term. And we're always going to assume that it's much smaller than Hx. So let's try to understand the two phases. So on this side is what I call the Higgs phase. So let's try to understand what this phase will be. So when your Gauss law term is 0, right, the dominant term in your Hamiltonian is literally just this Hx term. So your wave function, at this point exactly will be the all plus state, but will be pretty close to the all plus state throughout the range of parameters that I'm showing here. And you can think of that, you can write the all plus state as being up plus down, which just means that in like the graphical, electric field language that we wrote down earlier, the all plus state can be thought of as the equal weight superposition of all closed and open electric field strings. So, what that means is that the number of Gauss law violations in the system is sort of uncertain. And this is why we say that, this state is sort of condenses E anyons or condenses Gauss law violations or gauge charge. So it's like Bose-Einstein condensing, the anion. And we call this the Higgs phase. On the other side, when K is much bigger than, the on-site fields, the ground state will more or less satisfy the Gauss's law. And there are two phases that appear here. So the first phase, let's just take Hz to be, relatively large, then in this case, what I'll get is that I'll only get, it basically costs energy, right, in order to have an electric field. any length electric field. Because there's this Z term that penalizes downspins in the problem. And so my ground state will be some, like superposition of basically all spin, like no electric fields in the problem, and maybe small fluctuations of electric fields here and there, but very small, like confined fluctuations. And that's why it's called the confined phase. And then, at the very bottom, you'll see that there's this small sliver of toric code phase. It's really quite wimpy. And, the toric code is the equal weight superposition of all of the loops. And the reason why, this phase appears is because, there's this competition between, this on-site field, HZ, and this perturbatively generated resonance term that I brought up earlier. So in other words, this HX term is still there, and it violates the Gauss's law. But at fourth order in perturbation theory, you can be on resonance again, and you can generate this this plaquette term that can stabilize you against very, very weak on-site fields. So you can see like this goes down to like 0.25, like that's maybe the extent of 0.025 in HC. So that's the extent of on-site fields that you can stabilize with this resonance term. So the fact that both HZ and this plaquette term are really small in the problem should signal to you that, in this confined region of the phase diagram, there are lots of sort of phases, like there are lots of sort of states that all satisfy the Gauss's law that are kind of weakly split from one another, by these terms. It's just something to keep in mind. And I'd be remiss not to mention, the phase transitions between the Higgs phase and the toric code and the confined phase are second order phase transitions. They're specifically Ising star transitions. And then the transitions between the Higgs phase and confined is actually first order, and it's kind of unnecessary. So there's actually a crossover between the two. In this context. So now, that we have the ground state phase diagram, let's try to understand what's going to happen when we dynamically sweep from the Higgs phase to either of the Gauss law satisfying states. So let's not worry about whether it's, the toric code or whether it's the confined phase. Let's just try to, sweep into either confined phase. So
I'm sorry, Rahul, question.
Of course.
So just how do you, what is an order parameter you have on this diagram? Like how do you know if toric code is a toric code? Is it like some kind of Wilson loop or somehow, I don't know.
Yeah, so okay, I'll tell you the way we used it, the thing we did to get this phase diagram is that, so for these transitions, we look for divergences in the correlation length. So we actually use two independent methods to check the phase boundaries. So first we look for divergences of the correlation length. And then probably the more, principled approach is to compute this so-called Friedrichs-Hagen-Markov order parameter. The intuition behind it is really simple. So I told you that in the Higgs phase and the confined phase, you have anions being condensed, right? So in the Higgs phase, you have E anions being condensed. And in the confined phase, you have M anions being condensed. So what condensation means, right, of course, is that you get long range order in some 2-point function. Usually that's like the, kind of definition in, normal symmetry breaking. So for example, you get like ZZ being long range ordered in the Ising ferromagnet. But, in the case of anions, the thing that creates, the E anion, right, is of course the Wilson loop. So, there's some string, and that's made up of product of X. And at the end of it, right, it has two E anions at the end of it. And so naively, if you wanted to detect the existence of this Higgs phase, what you would do is that you would, make this, string really, really long and check, oh, are my E anions condensed? The only problem is that, these strings all carry a line tension in them, so they always will decay to 0. So to actually fix that, what you do is you normalize by the square root of the closed loop, that's twice the length, if that makes sense. So that kills the string tension decay, right? But it checks for the long range order. So you check for the existence of the toric code by looking for the absence of condensation of either the E or the M anion. Does that answer your question? Like these are.
Yeah, that's super good. That's super good.
Okay.
Thank you so much.
Yeah. Okay, awesome. So yeah, so what we're going to do is we're going to start in the Higgs phase at k equals 0, and then we're going to sweep at some rate t into a Gauss law satisfying state. So our Hamiltonian will look something like this. So we'll have a linear sweep from k equals 0 to k max, which in this case is 4, 4 over hx, I should say. And yes. And the claim is that this, the thing that I want to show you today is that dynamically sweeping, in a particular window of rates, will prepare something like a quantum spin liquid phase. So how do we start to think, kind of physically about what's happening as we go across this transition? So in order to gain some intuition on the dynamics of the system, one way that I like to sort of think about it is in terms of by examining the sort of level structure of the system. So this, you can look at the level structure, for example, in exact diagonalization. But again, this is just a heuristic to kind of keep in mind. There are ways to make these things a little bit more formal, but it's just a way to sort of think about the problem. So in particular, we now have two sorts of phases, right, in our spectrum. So we have our Higgs phase on one side. So we can tell it's the Higgs because it's a unique ground state. It's well gapped above, its excitations, and it's on this side of the transition. On the other side, right, I told you earlier that, the things that were splitting different Gauss law equivalent, Gauss law satisfying configurations, were very small terms in the Hamiltonian. As a result, there are these many states that are all very close in energy to the ground state, when you get to either Gauss law phase. So in other words, all of these things are sort of competing with one another very closely. So already you can kind of, just by kind of looking at this, you can see that there's sort of two distinct branches of states. So there's like a V-shaped branch of states, it like goes down and then goes up. And then there's this hockey stick shaped branch of states, that just joins the ground state manifold. And so, let's just label these. So we'll call this the so-called E anion branch. The reason we'll call it this is because actually it includes the E anion that uncondenses as you go across the transition, right, in the second order case. And then we have also an M anion branch of states. So these are states that are sort of, all satisfy the Gauss's law, right? So and these things are sort of split in general by the local energy scales in the problem and times the total system size.
Just make sure those hockey shape that those states join the earlier unique ground state, are those topological degeneracy?
No. That's a very good question. So it's not. So so the numerics I did in this case were actually, they were on a torus. So it could conceivably be, a ground state degeneracy, but these are all states that satisfy the Gauss's law, these are just states that satisfy the Gauss's law. So in the case of the toric code, closed loop states would all sort of be competing at low energies with one another, right? Because the thing that splits them in energy, right, are these very tiny, like on-site fields, and a small tiny resonance term that will pick out certain superpositions over other superpositions. Does that make sense?
So what's the ground state, or what's those states, maybe the wave function look like for those who join the...
Yeah, of course. So in the case of the toric code, the wave functions would look like, for example, I'll just draw one state. So this is an example of a state. So it's just a closed loop state. Another example is a sum over a couple of closed loop states could be in the ground state manifold. The point is just no open strings, right? That's the only rule that's in here. So there's lots and lots of states that are here. You can see it's a very dense mesh. Does that sort of answer your question?
But how do they count the different ground state? Shouldn't they? I mean, I'm not sure I really get the point. Sorry.
Oh yeah, of course. Sorry. I should specify that this phase is not a quantum spin liquid. So the ground state here could be the confined phase. Like for example, the ground state could be all of the spins pointing down, or all of the spins pointing up, for example, right? Does that kind of make sense? So there's no when you're looking at the spectrum here, you're really looking at like a really large number of states, like not just 4, 5, 6, something like this. You're looking at like, I think this is 200 states or something like this. That's shown here.
Okay.
So I have a question.
Yeah, of course.
Is this charge at hz equals 0?
Sorry.
Is this charge at hz equals 0?
No, it's not. Yeah, it's just small system size numerics. That's why.
Okay.
It's small. Yeah. Okay. Does that answer your question, Juven? Kind of. It's just the basic idea is that when your Gauss, imagine your Gauss law term is the only term in the Hamiltonian, right? So the only term you have in your Hamiltonian is z's, kind of going around a vertex, then every state that, has this being +1, so the only term in the Hamiltonian is this, then every state that has this being +1 will be, at 0 energy, or sorry, will be in the ground state, right? And that's a really large number of states, and now if you add a really tiny term that splits them, if you add a really tiny term that splits them, then you'll have, for a really small system, which is the thing that's shown here. Of course, for an extensive system, you'll, these things will kind of blow up and stuff like this. But for a very small system, you know what I mean? All of the states will sort of be split very weakly from one another. And certainly it's true that the local gap between any two states will be small. Okay, I'm hoping that's fine. Yeah, so,
So you call it Gauss law phase.
Yeah, all I mean by that is it could be either the deconfined phase or the confined phase.
Okay.
Yeah. Cool. Yeah. Yeah. Sorry, I didn't specify that. Yeah. So, okay, when we're thinking about, now that we kind of have some understanding of what the spectrum kind of looks like, it's kind of useful to recall sort of two traditional regimes of dynamical parameter sweeps. So let me clear my drawings. Two traditional regimes. So, at the very bottom, like, let's say that this is my spectrum of states, if I'm traveling at a rate, if I sweep the parameters in my Hamiltonian at a rate that is much smaller than the energy gap, for example, right? This is called the so-called adiabatic regime. So there, my wave function as a function of total time will be approximately equal to whatever the ground state is instantaneously in my system. On the other hand, if I sweep my parameters very, very fast, then I will, if I sweep my parameters very, very fast, then I'll enter into this so-called sudden regime, where the wave function that I generate at the very end, will be equal to the wave function, that I started with. In other words, I'm changing the parameters in my Hamiltonian so fast that my system is not able to respond to it. Yeah. So, now that we sort of have an understanding of these two regimes, let's just sort of imagine that we, sweep across the transition at a rate that's adiabatic relative to the sort of like at a rate that's quasi-adiabatic relative to the like E anyons in the system, but sudden relative to the M anyons in the system. So what I mean by that is, that, if you do this, then basically you start off in a phase where you've condensed your gauge charge. And so you have some large occupancy of gauge charge in your ground state. And, slowly as you tune the parameters across the transition, right, for this very small size system, but of course I'll discuss what will happen as you go to larger size system, right? Your wave function will be orthogonal to the, sort of E anyon branch of the system. So you'll equilibrate out the condensed E, right? Because as you uncondense the E across the transition, right? But since your dynamics is fast relative to the M anyons, you'll avoid nucleating in the M anyons as you like cross the transition. So in other words, the dynamics in the sort of like you equilibrate out the E anyon but you fail to nucleate in the M anyon if it's proliferated in the ground state. Because you're just sort of out of equilibrium relative to the dynamics of the M anyon. So, this sort of motivates a very simple conjecture for what you can imagine the final state of the system is. Basically, the only dynamics in the system is projecting out, sort of E anyon degrees of freedom, because the M anyon sector of the theory is sort of frozen. And so what we'll have is that the final wave function will be, sort of proportional to the initial wave function, but we project out all of the Gauss law violations in the system. And so in this sense, we say that we dynamically un-Higgs the system, right? Because we've taken, a state that has, condensed gauge charge, and we've gotten rid of the gauge charge. And so, in the kind of spirit of the two regimes that we showed earlier, this kind of highlights a kind of novel, regime of dynamical sweeps, right? Where you're sort of between the two, conventional paradigms. So in other words, you're in this so-called hemidiabatic regime. I think hemi is like Greek for halfway. In this regime, you sort of project out, you remain orthogonal to the charge degrees of freedom that you're adiabatic relative to, but you are sudden relative to the flux degrees of freedom in your problem. So yeah, you're slow with respect to E and fast with respect to M. And this window is sort of characterized by two timescales, TE and TM, where this TE is associated with the inverse, is basically the rate associated with the gap to your charge degrees of freedom. and Tm is the rate associated with the gap to your flux degrees of freedom. So in other words, you're in this window if your rates are sort of between these two. So let's test this conjecture, kind of, in a many-body context, right? So far, what I've been talking about is sort of small system size things, but let's test this conjecture in sort of a many-body setting. So how do we test it? We'll take our Hamiltonian, which is, consists of these three terms. So again, we have our Gauss law constraint, the thing that generates E and the thing that generates M. And what we'll do is, actually this conjecture sort of makes three very striking predictions. So in particular, so the first thing that you would imagine, right, is if this was true, then there would exist a time, like a rate, below which, a rate below which you would, be in equilibrium relative to the E degrees of freedom, right? So that is to say that the total time of your sweep, if you go slower, right, you fully equilibrate out your E degrees of freedom, and then nothing happens beyond that. And so you'd expect that, as you go past TE, you should be insensitive to, the generation of M anyons, for example. Like this quantity should be insensitive to the generation of M anyons because it just knows about the dynamics of the E anyons. On the other hand, you would expect that this projected overlap quantity that I told you about, yes, someone's asking a question.
Hank, please.
Yeah, so can you go one slide before?
Mm-hmm.
So maybe this is just a very basic question, but if you sweep across the toric code regime, right? Let's say you just stay on that line and you sweep across that phase transition, then wouldn't the gap close here?
Yes, no, you're definitely right. So yeah, so actually it turns out that so I'll present a little bit more of a nuanced take on this. This is just to provide some high level intuition for what's going on. But I mean, the basic idea is that, yes, as you cross the phase transition, you'll fall out of equilibrium relative to the charge degree of freedom, precisely because the gap closes. But you'll get sort of physics that's similar to Kibble-Zurich, right? That is to say that you'll have this sort of frozen regime where your charges are frozen, and then you'll equilibrate out, on the other side, of the transition, and you'll have some low density of defects. It's kind of like if you sweep, from the paramagnetic phase to the ferromagnetic phase in the icing model, then you'll have, you'll still realize a phase that looks kind of like the icing phase, but with domain walls and things like this. Some domain wall defects in your problem. Does that kind of make sense?
So that's the fact that you're kind of the fact that these kind of domain walls, as you're saying, are manifesting is because the gap do close.
Yeah, the gap to the charges does close, but I think the key point is that on either side of the transition, right, the dynamics of the E anyons is very fast, right? It's set by large energy scales in the problem, right? This is to be in contrasted with the M anyons, right? Right, which the moment you fall out of equilibrium relative to the M anyons, you stay out of equilibrium relative to them. So, yeah.
Okay.
Yeah.
Thank you.
Yeah, of course. So awesome. So so the first conjecture is that we would expect that the Gauss law, if we measure the Gauss's law, right, as we go slower, right, this makes sense. You should start satisfying the Gauss's law as you go into the Gauss law satisfying phase. Either the deconfined phase or the confined phase. Similarly, this projected overlap quantity that I told you about, remember, there's this sweet spot, right, where you expect this projection formula to hold, right? Which is when you're slow relative to the dynamics of E anyons, but fast relative to the dynamics of M anyons. So basically, around the time when you start being in equilibrium relative to the charges in your problem, this quantity should start increasing. That's the first prediction. And the next thing is that by increasing the rate at which you generate M anyons, by increasing this term in the Hamiltonian, right, a larger energy scale in the Hamiltonian will correspond to a faster rate. You should be able to squeeze this window, this TE-TM window, together. And you should see this window get smaller, basically. And then there's this other, sort of procedure that you can check that I think is really non-trivial for the existence of this separation of scales. So in particular, the thing that you can check is imagine starting off in the fixed point of the Higgs phase, and then sweeping to the final point of your sweep, and then sweeping back. If you were perfectly adiabatic the whole time, you would return back to the wave function that you had. Similarly, if you were perfectly sudden both times, right, you would return back to the wave function that you had because nothing happened during the dynamics, right? But it's very non-trivial for you to return back to the exact wave function that you had, or similar to the, have a high overlap density with the wave function you had if you're in some intermediate regime. And so what we would expect is actually to see kind of two clean dips, right as you transition out of the fully adiabatic regime, right? Or sorry, the fully sudden regime to the fully adiabatic regime. And then you would expect a hump in the middle, right? Associated with this adiabatic relative to one degree of freedom and sudden relative to another degree of freedom. Yeah. And you would expect again that I can tune the size of this window by increasing the value of HZ. And indeed, if you do numerics, so we did, we did just time dynamics using cylinder matrix product states, in particular, like the W2 method. It's like an MPO method. If you do this, you indeed find the predictions that we saw. So these different colors are increasing values of HZ. So you can see as I increase the value, so the value of the Gauss's law is sort of insensitive to the value of HZ, right? Purely because HZ just controls the dynamics of M anyons and doesn't control, the equilibration of E anyons. On the other hand, as we increase the value of HZ in this case, we can see that, this projected overlap is kind of nearly maximal, and then it just drops down, quite rapidly, kind of signaling that this TM and scale is moving to the right as I increase HZ. And I think this is really beautiful. You can see, if you check this revival amplitude or this like echo amplitude, you'll see that, there's this regime where both of them are sudden. There's this regime where both are adiabatic, and then there's this really clean regime in the middle where you see that E is sort of, your adiabatic relative to one degree of freedom and sort of sudden relative to the other degree of freedom. So, I'll get into, it seems like there's lots of questions on formalizing this this intermediate regime in just a second, but the nice thing about this is that in this like sort of intermediate regime, you can use the projection formula that we sort of wrote down to get an analytical handle on the non-equilibrium dynamics of the system. So that's kind of, non-trivial, right? So if you take, the assumptions of the, if you're in the regime where, the assumptions that go into the projection formula hold, you can actually use it to predict, in what situations will you actually get, a quantum spin liquid out. So in particular, at HZ equals 0, your state looks like this. Your state looks something like this, which is the all plus state, which, if you recall, is the sum of all closed and open loop strings. So if you do the projection formula, if you assume that this is true, then what you'll get is that this projection applied to, this initial state, just projects out all open strings, and you indeed just get the toric code state. And we can do a little bit better than that, actually. We can ask the question, okay, at finite HZ, when do I get a quantum spin liquid out when I do my, my dynamical sweep? So in particular, we start off in the initial state, psi of 0, which is, cosine theta plus sine theta minus. You can always write it as this when you're on this line. So again, we're at this line, and the wave function can always be parameterized as this, where theta is this. And then you can exactly rewrite it in terms of the all plus state, and then a factor that looks like e to the beta over 2, times the sum over all z's. Basically, what this does is that this thing generates flips, like this generates a flip of the plus state. And so this is kind of an exact reparameterization of this formula right here. And so if we apply the projection formula, since the projector is just a product of 1 plus GV over 2, like the Gauss law over 2, and the Gauss law is just purely diagonal, it commutes with this Z. And so, when you act on it, you get the, you can pass it through and you get the projector acting on the plus state, which is the toric code. And then to determine for what beta this is topologically ordered, you can use Kramers-Wanier. So in particular, we're going to do Kramers-Wanier between the links of the square lattice, which is where our toric code was defined, to the plaquettes of the square lattice. So yeah, it looks something like this. So Z moves to ZZ, and then the product of X around a plaquette will become X at the center of the plaquette. And if you do this, it's not super hard to show that this wave function that you wrote down will go to the following wave function. So the sort of way to see that is, so, Z goes to ZZ, so that's clear, right? But the other thing, so we want to see why the toric code state goes to the all plus state under this Kramers-Wannier duality. Well, the reason is that if you make the star operator, actually, and that actually becomes 1, like literally the number 1, right? In the Plaquette language, right? Because Z will just product, pairs of Z's around a loop, which will just product to 1. So you already have that stabilizer satisfied. And if this stabilizer is equal to 1, so, then that means, under the Kramers-Wannier duality, that just means that the state you're doing is the unique state that's stabilized by X, which is the plus state. That's the way to see it. So this state is really quite interesting because it's like this projected phase looks like a state with the correlation, whose diagonal correlations look like the correlations of the classical Ising model. And you'll basically find that the topologically ordered phase of on one side of the Kramers-Wannier duality maps to the disordered phase of the classical Ising model, which is kind of very standard. And the transition out of the QSL occurs precisely where you transition from the disordered phase to the ordered phase on the other side. So that occurs at HZ over HX is approximately 0.46. So I did the reparameterization. And so you can see the regime in which this projected state would in principle prepare a topologically ordered phase is much larger than the regime that this that the toric code is actually in the ground state. So, okay, yes, this is the question that people have asked. So how does our method scale as you go to the thermodynamic limit? So, recall that as someone else pointed out, I think Hank pointed out, the local gap to E excitations goes to 0 across the transition as 1 over L. And similarly, the local gap to M-anion excitations, right, always remains sort of finite. And it's set by these small energy scales, Hz plus Hx to the 4th over K cubed, roughly. So in the thermodynamic limit, it's no longer possible to be perfectly slow with respect to E and fast with respect to M, right? Because you have a sort of energy scale that's going down to 0, and you have another energy scale that remains finite. So there's going to be some time where you squeeze to this. And so, the best you can actually end up doing is you can go as slow with respect to E as possible while being fast with respect to M. And basically what you'll end up doing is that you'll end up, you'll get sort of the analog of Kibble-Zurich physics. And we have some evidence for this. So in particular, what you'll get is that you'll start with your fully, condensed E state, so your Higgs state, and slowly you'll try to equilibrate as much of the E's out as possible. At the transition, the populations of E's will become frozen. And then on the other side of the transition, you go through what's called Kibble-Zurich coarse graining, right? And you'll form a state that has a dilute density of E particles. Essentially, right, E's cost energy on the other side of the transition, right? And since you're not pumping that much energy into the system by doing slow time dynamics, right? You can't have that many E's in your final state. That's kind of the high level intuition. And this is why you get these sorts of effects. So, so it's no longer possible to be perfectly slow with respect to E, but what you would expect is that, the E anion density is set by a Kibble-Zurich type phenomena, and it's determined purely by the rate at which you cross the transition. So it doesn't really matter how much time you spend after the transition, provided that you've equilibrated and coarse grained, right? But it's set by the speed at which you cross the transition, the vicinity of the transition. On the other hand, the amount of M anions you nucleate, you would expect to be set by the amount of time you spend after you cross the transition. So the M anion only becomes well-defined, when you're on the, other side of the transition in some sense, right? So it's like a gapped spectator at the critical point. And so basically, as you're crossing after you cross, the phase transition, that's the only time when you can start to nucleate in the M particles, and if you spend more and more time, you have this small energy scale that's multiplied by a large time scale, and you'll nucleate in more, M anions into your system. And so you can actually check this in numeric. So one way to kind of check this is, so you would expect that if the first statement was true, if you looked at the Gauss's law for 2 different rates, you would see that as I go for slower rates, the Gauss's law will improve. So indeed, that's what we see. As you cross the transition, right? Here's the location of the transition, this dashed black line. After you cross the transition, you quickly coarse grain into the maximum value of G, more or less, and then you just kind of park, at a place that's set by the rate that you cross the transition by. This is sort of, it's certainly not fully Kibble-Zurich, I should say, like Kibble-Zerk comes with a lot of baggage to it, but it's just consistent with the idea that the rate that you cross the transition is what determines, the sort of final density of E anyons. On the other side, we have we can ask, once we've crossed the transition, it's clear that the E anyons aren't doing very much, right? So we can ask, what does the projected overlap do? And so the only thing that could ruin the projected overlap, if the E anyons are kind of, equilibrated out, is the proliferation of M anyons. And we basically see that the projected overlap is ruined at a rate that's sort of linear with respect to the energy scale associated with the, E anyons, and it doesn't depend on the rate that you cross the transition. So it only depends on the sort of time that you spend after the transition. So the transition time for this rate is right here, and the transition time for this rate is right here. And you can see, that the amount that you go down only depends, they peak at roughly the same location, and the amount that you go down depends on the amount of time you spend past the transition. Yeah, I hope that makes sense. So are there any questions on the first part? I think how am I on time, Juven?
Is it better to cross the transition through the first order line or through the second order, like a torical phase?
Yeah, that's a good question. So yeah, that's something that I didn't comment on in my slides just here. So yeah, you're right that there are two, sort of transition. So the thing is that, as you're crossing, between the first order and, let me go back to the phase diagram. So as you go from here to here, the spectrum of your theory doesn't really change very much. The reason that you get this first order transition, instead of, two second order transitions is really because of a level crossing, in the Gauss law satisfying states, of your system. Does that sort of make sense? So in terms of the dynamics, the energetics of the system look very similar. And indeed, if you actually there's kind of no signature of the existence of a first order transition, as you cross this. It's kind of similar to the idea of supercooling. If you know this, if you kind of go too fast through a first order transition, you sort of jump the gap and you're sort of insensitive to it. And then after some time, you're very susceptible to false vacuum decay, for example. Does that answer your question?
Yeah, but in the second, if you go through second order transition, maybe there's Kibble-Zerk scaling, right? The correlation length scales with your tuning speed with a certain power law, but that is not expected in the first order transition. Is there a difference?
So, yeah, that's a very good question. So let's think about what happens, as you go between the first order transition and the second order transition. So you would basically expect that the energy scale associated, so if this is your Higgs phase, for this line versus this line, a very small parameter in my Hamiltonian has changed. So I would still expect that the energy scale associated with, the gap to the E anyons won't change very much. Or sorry, this is the conjugate, the disorder parameter for the Higgs phase, right? So it will still go down, whether or not exactly closes and things like this, right, is a different question. But if you're traveling across the transition at a finite rate, you're sort of insensitive to the fact of what happens exactly at the transition, right? You're sort of, only sensitive to the, sort of near transition energetics. Does that sort of make sense?
Yeah. Thank you.
Yeah, of course. Awesome. Does anyone else have any questions before I move to experiments? I don't know. Again, Juven, how am I doing on time?
It's about time, but I guess you can still go through the part you prepare.
Oh, okay. Yeah. Let me try to be quick then. Okay. Yeah. Thank you guys so much for the wonderful questions. I'm sorry for keeping you longer. So okay, let me quickly just go through this this experiment. How our work sort of connects to the experiments. So basically, there's this recent Rydberg atom experiment that saw signatures of a Z2 quantum spin liquid. And it was done in the group of Misha Lukin in this paper by Giulia Samaghini et al. In 2021. And just as a broad strokes, background on the experiment was done on what's called a Rydberg atom array, which consists of rubidium-87 atoms trapped in optical tweezers. So the basic idea of a Rydberg atom experiment is that you have these rubidium-87 atoms. And if you excite them to their Rydberg state, which is just a state that has a really high principal quantum number, so that means that the electron, is sort of very far away, and you have some, large dipole matrix element, then atoms, two atoms that are in their Rydberg states kind of interact very strongly with one another within a radius that's called the blockade radius. So in other words, if I have two atoms that are within the blockade radius, this is the sort of energy penalty they pay, but outside of the blockade radius, they don't pay very much energy at all. And the Hamiltonian that governs the interactions between Rydberg atoms is just an Ising-like Hamiltonian. So it consists of a Rabi drive, what's called a Rabi drive, which is just a sigma x term. It consists of like a chemical potential sort of detuning term. And also, finally, it consists of a long-range interaction term that interacts with this sort of 1 on r to the 6 potential that's shown in this box. And the basic idea is that, if you place atoms on the bonds of the Kagame lattice and you tune the blockade radius to be a certain distance, then basically what I can do is I can make it so that atoms that share a that are neighboring the same vertex don't want to be mutually excited. So in other words, if an atom here is here and an atom is here, I wouldn't want them to both be mutually excited next to each other. And so in that sense, I can, kind of think of my atoms as dimers, that don't want to share a vertex. And as a result, this realizes a so-called emergent dimer monomer model. So, it's okay to not have, it's okay to have an unoccupied vertex, but it's not okay to have two things touching each other because of the blockade constraint. And, since this is an emergent dimer model, it has the potential to host an odd Z2 quantum spin liquid, which is very similar to a even Z2 quantum spin liquid with some notable differences. The thing that I'll care about here is just that, the Gauss law around any given vertex is equal to 1 instead of 0. And so, now it's just a question of, now that you have this like emergent dimer monomer model, it's just a question of picking the right geometry and asking the question, does your ground state actually realize a quantum spin liquid? And if you take the experimental geometry, so this is the geometry that they were using in the experiment, you can see that this is the normal Kagame lattice. And then I just put qubits at the links of them. If I do that, you can actually show that the long range tails of the Rydberg interaction actually confine my quantum spin liquid. So there's no quantum spin liquid in the phase diagram, and it's confined from the long range tails. And as a kind of remark, if you slightly modify the geometry by just breathing the lattice a little bit, you can actually get a quantum spin liquid out. So, nevertheless, despite the fact that there was no ground state spin liquid in the system, the experiment saw remarkably clean signatures of a quantum spin liquid phase. And, the sort of reason for this is because, they started off, in the trivial Higgs phase, and they swept into a phase that satisfied the Gauss's law, which in this case is the valence bond solid phase of the experiment. And, it's sort of been appreciated for a while since the experiment came out that time evolution would capture the phenomenology of the experiment. And indeed, in the supplementary of the experimental paper and a follow-up PRL, they just did numerics, and they showed that if you simulate the experiment, you indeed get, you indeed are able to reproduce the phenomenology of the experiment, including the really nice, quantum spin liquid signatures. But the thing that we sort of showed in our paper is that first we showed that the regime that the experiment is in, is precisely the regime in which you would expect our mechanism to sort of hold. In particular, you can actually painstakingly estimate the local energy gap for M anyons by doing a very careful counting of the Rydberg interaction analytically, and show that the scale of M anyons in the system is about 100 times smaller than the scale of E anyons, at a comparable point of the phase, in the phase diagram. In addition, we verified that our projection formula would indeed analytically predict the existence of a quantum spin liquid. And furthermore, actually, it turns out that our theory kind of motivates a numerical tool for reproducing the experimental data just as well as full scale numerics, but 3 orders of magnitude faster. So I'll just quickly talk about this. So a kind of striking prediction of our theory was that earlier on I told you that there were 2 requirements for quantum spin liquids, namely strong Gauss's laws, and in addition, strong quantum resonances yielding quantum superpositions. But the out of equilibrium mechanism I told you relied only on the dynamics of M anyons being approximately flat, like being very slow. So the prediction is that resonances aren't really necessary, right? We don't need energy scales penalizing or or giving dynamics to the M anyons. And so, a kind of, way that you can think about this is that, even the perturbative resonances that you generate, right, are quite small, but they're generated, at an order of perturbation theory associated with the plaquette size. So the plaquette size here is 4, and that's why this is associated with, a 4, site resonance, a 4th order resonance. But, if the plaquette size is 6, you'll generate a 6th order resonance, for example. And so one way to get rid of the plaquette resonances is to actually take the limit where the plaquette size is infinity and put the system on a tree. So you'll see that this looks a lot like, the bonds of the Kagame lattice, the Ruby lattice, but crucially, it never loops back on itself. And it's just infinitely repeating. So, I guess the prediction of our theory would be that a tree should well approximate the dynamics of the normal lattice in this circumstance, sort of because, the things that we've thrown away, when we've, sort of cooked up this tree, are sort of irrelevant to the dynamics that's going on, like are sort of frozen. So, the nice thing is that if you put the system on a tree, you can actually really nicely, efficiently numerically simulate it by the use of tree tensor network numerics. And for those of you kind of familiar with like tensor networks, the reason for this is because these tree tensor networks, don't have closed loops, and as a result, you can define a nice definition of the canonical form similar to 1D, the 1D matrix product state. Oh, yes, Roger.
On a tree tensor network, they aren't actually flux excitations, right?
Yeah.
So like there's no sense of flux condensation. You've just merged two phases into one.
Well, no. So you can ask the question, right? That's a very good question. So, in some sense, you can think of the plaquettes as being kind of infinitely big. So one thing you can ask is, I can define, I don't know if you're familiar with the original paper for this Ruby lattice experiment, but you can define these like gauge theory operators, right? Like you can define the analog of like, the kind of M string, and you can have it go out to infinity, right? If that makes sense, like you can have it sort of, and the way you compute that in the tree tensor network is by computing the transfer matrix and inserting a value of the kind of toothed line, between, and then computing the largest transfer matrix eigenvalue of that. And that kind of gives you a proxy for, the value of this, like, like flux, you know what I mean, in the system. Does that kind of make sense? Like, there is still a distinction between like the confined phase there is still a distinction between the confined phase in the system and the Higgs phase in the system and the deconfined phase in the system. Whether or not the deconfined phase on a tree is stable or not, is something that I don't want to get into, but I don't want to comment on, but in some sense, the deconfined phase in this case will break. The confined phase, corresponds to the VBS, which breaks symmetries. The Higgs phase will not satisfy the Gauss's law, which is still a local quantity on the tree. The deconfined phase won't break any symmetries and also won't. Does that answer your question?
I think so.
Okay. Yeah, I just mean to say that there's still a distinction between these things. Do you kind of see like the valence bond solid will have to, break the translation symmetry of the system because the M anion kind of, carries a projective representation under the translation. Yeah, and in the odd Z2 gauge theory case. I agree. It's a little bit of a subtle point, and maybe we can talk offline on that. But in any case, if you do these, tree tensor network numerics, so the matrix product state numerics are the light yellow line here. The tree tensor network numerics are the dark orange line, and then the experimental data is the black line. So if you're having trouble seeing the difference between these things, it's because they match very, very well. But the tree tensor network numerics take about 3 minutes, whereas the matrix product state simulations took about 3 days to do. And you can see that even at the level of like just the probabilities of the different dimers that appear, the matrix product state simulations and the tree tensor network simulations kind of match remarkably well, and they deviate kind of in the same systematic way from the experiment. And this suggests that there are things in the experiment that at the level of modeling that we don't understand, for example. So okay, with that, I'll quickly conclude. So, I hope that I convinced you that, there's this interesting non-equilibrium mechanism, that can effectively dynamically project out, anyons. So dynamically un-Higgs the theory. And also, I hope I convinced you that this is sort of related to the experiment, the Rydberg atom experiment. Something that I didn't mention is that, we also did some additional numerics to show that, you can prepare spin lakes that have no stable equilibrium analog. So, for example, the 2 + 1 du1 quantum spin liquid without, is unstable, to, monopole fluctuations. And it only appears as a fine-tuned point called the RK point. Nevertheless, by putting Rydbergs on the Kagame lattice, on the vertices of the Kagame lattice, you can actually, and doing dynamical sweeps, you can actually stably realize this phase. So, or realize this state, the fine-tuned RK state. Yeah, and this comes with a sort of new experimental proposal that we did. And just for some future directions, the thing that we've been trying to think about is, characterizing the class of lakeable quantum orders, placing the projection formula on a bit of a rigorous theoretical footing. It's definitely, just kind of a heuristic ansatz for what the state should be right now. And in addition, we're kind of further exploring the applications of, the possibility of dynamically implementing something like a projection operator. So it seems like we have some preliminary numerical evidence that, you can do things like even Gutzwiller projection by sort of using the ideas used here. So with that, I want to thank my collaborators once more, and thank you guys so much for your attention and staying longer. So yeah.
Thank you very much. Thank you, Rahul.
Yes.
Thanks, Simoni.
Yes, thanks. Yes, I have a question. Could you explain a bit how, how do you map the physical lattice into the three-tensor network structure? Because it was not clear to me. Thanks.
Oh yeah, of course. So here, okay. So let's try to see. So for example, you can see that like this lattice that I've drawn here, this is called the Husimi practice lattice, right? Locally has the structure of the Ruby lattice. Does that make sense? But the only thing that happens is that basically, in this case, I can actually go in a loop, but essentially here, I do the same thing, but I can't quite go into a loop. Does that make sense? Like it just doesn't wrap back onto itself.
But so where are the tensors?
Oh yeah, where are the tensors? Oh, I see. Yes, that makes sense. So if you work in the blockaded model, the local Hilbert space, you can actually encode in one of the triangles. So there are 4 possibilities. The dimer can be, on any 3 of the bonds, and then also it can be all empty. So you have a 4-site local Hilbert space. And then we impose the blockade constraint between the triangles in a soft way by including a, interaction that's like 20 times bigger than anything else. Does that make sense? So the tensors really sit at the center of the triangles. So they form a beta lattice.
Okay, so each vertex of the triangle is a tensor, in your structure.
Yeah.
Okay.
Yeah.
Okay, thanks.
Yeah, of course.
Okay.
There's one more question, raised hand. Oh, no. Does anyone else have any questions?
Any more question?